Բացել էի New Ripsի best paper-ները, այնտեղ runner paper էր հանդիսանում։ Ոնց է անում, որ փակվում էր։ Ինչ։ Լավ։ Ո՞նց է կարամ։ Անգլերենով չէ։ Լավ, անգլերենով կպատմեմ։ Hello, today I will present the last New Rip's paper, which called Rho. This is called Rho because Rho, it is the way how they use information from all over the tokens. And this paper was one of the one level below best paper in New Rip's. The authors are from Chinese labs and from Microsoft. So, motivation. Today, if we want to boost models' performance, usually we scale up models' parameters and data size. And when we want to get more data, the data in internet is usually very noisy. And if we want to train on all available data, it's not optimal or even feasible. That's when people are doing many document level filtering, but even if documents are in high quality, even in that kind of documents, there are many noise. So for example, in this sentence, it could be normal sentence, but there could be some tags or usernames that are not important for training. So usually people can just remove those tokens, but it could somehow alter sentence meaning. They can remove whole sentence, but it could remove useful information. So the authors suggested, what if we can choose on which tokens to train our model during pre-training phase? But first of all, to do such kind of training, they go and explore what are the token level training dynamics of the tokens. So the initial setup, they choose already pre-trained tiny llama, which is 1 billion, and they choose some kind of pre-training corpus, which is 15 billion token. And they took checkpoint over 1 billion tokens training. And then they evaluate 320,000 tokens. So they calculated this much of tokens statistics. At the end, they group tokens, and they see that they group in 4 categories. Like there are 4 groups of tokens. If we see the majority of tokens are the tokens which loss were low, and after the training they still remain they still have lower loss. They are 50%. And then they are high to high loss tokens, which are some kind of resist convergence. There are low to high, and the most important tokens here are the tokens which are grow from high to low. They are learnable tokens. And they will, I will show you. So the high is like they're at the first checkpoint, they have high loss, and at the last checkpoint, they also have high loss. They loss, yeah. So it was the first observation. The second observation is that like low to low and high to high tokens, they have a lot of fluctuations and high variance. So they could even damage our training dynamic. And how we can calculate these groups. So this is the training dynamic of just one token, how it's evolved, how its loss evolved, and what they do. They take every token's losses, and then for every token, they calculate it just they fit linear model to it and just got some kind of line. Then they calculated the last and the first points difference, and also the mean of the last checkpoints of all tokens. Then they say that they define the tokens that's the difference between the end loss and the start loss is if it's smaller than minus 0.2, they call this high to low. If it's high, means it's get higher loss. They define it as low to high. And if it remain in the range of this, they define it as high to high or low to low. Yeah, and it depends on just the L mean that they calculated at the last checkpoints, the last checkpoint losses of all tokens.
So high to low, it's not absolute. It could be, it could start from very low, and then get lower than 0.2. That would be considered as high to low.
But after linear fitting.
Yeah, after linear.
Yeah. Okay. They somehow smooth.
So high to low is essentially contains the tokens that are getting better in the trend over the course of the training, but more than 0.2. Low to high is the opposite. How is regression is defined from
how does regression? They calculate it for each token.
Value also AD at the right side.
Yeah, the ln is the losses checkpoint loss.
Why not use the action point?
Because there are many fluctuations, and if you just get this one, it may be not good value for it if it's got higher or lower in here. That's why. Does that make sense? Any other questions?
So for the graph on the left, at each step, they just categorize a good token, and then they show the average loss for each category.
Yeah.
And how they calculate for the first step?
For the first step, they don't. They just like save checkpoints. They calculate it for all. They take all checkpoints and then calculate the trend.
So it doesn't start from 0, it starts from 1 billion tokens.
1 billion tokens, you can calculate it.
They train on this, but they calculate it on evaluation set, which is 300,000 tokens. This is the training dynamics, but the evaluation, these points are from evaluation set.
On the third line, there is some LNI. Is this the total?
ln is the last point of every token's loss, and I is the just one token's loss, and we just get the average of all the last token's losses.
This is for defining the high to high.
Yeah, only for this.
It's far too low, it might be in different places.
Yeah. Mm-hmm.
But in reality, they start from the same thing, almost the same. I think from the left.
Yeah. On average, green and blue start from the same. Like basically L to L is something like the token. Also.
Yeah, and so this is an example of just how we can categorize this actual in text. So there are so many, so this much categories in just one sample. And
this was found on Wikipedia. W is one token, the rest is. When you say this was found on W, it's definitely Wikipedia.
Okay, then. So doesn't recognize the formula.
This doesn't mean, right? This doesn't mean, this is just part of higher level based on context, right?
Yeah, but the question is that when you say, I don't know, the third line from the bottom, and there are some good videos on YouTube that demonstrate how to synthesize. So when you say there are some good videos, then on YouTube, it's so obvious that you don't even want to train on this text.
During the evaluation, they mentioned passing the one token, they passing the context of the token.
They pass whole sentences, but then for gradient passing, they choose only the ones which are learnable.
For gradient passing, for calculation.
No, for evaluation. Yeah, they did everything.
Oh, the last sentence is weird that you from the archive divide. Where is one?
I think the most important is L to L, that is useless.
That's what I'm trying to say. The token as can have a different value. It's not, it's at the beginning of the sentence, not at the end of the sentence, right?
I think
method is not that much expensive, but something else would have a big difference. Right?
Yeah, but I think the idea is in the loss actually. So if you know that the loss for this thing is very low, why do you want to do another gradient update for that easy function? I think that's the point here. But here, let's see what is the algorithm. My guess is that L to L will be ignored.
And also one more observation is that all these pre-trained data, not all tokens are equally important for already downstream tasks. This is for validation loss and validation set, but for downstream tasks, they all be different. That's why it's important to explore all the tokens dynamics to understand which one to choose.
passive, it's like high to low. Yeah, because when
It's
you place
complex.
go forward, yeah, but what are you gonna do with that? Passive all the time? No.
No, you're not.
Says to forward, you're going to do greater than double. But by the end of the sentence, we do. Because that teaches you something.
You don't know about it after.
Yeah, so that's another, we're only taking the
back.
we'll see the algorithm. I think, if I remember correctly, they're doing something with small model.
Not small, but with a reference model. They are. I will explain this part. This is just an observation.
So these categories are context dependent. Yes, very well.
Yes, and also they can differ from checkpoint to checkpoint. So what we observed that like during pre-training, not all tokens are decreasing smoothly. And that's why they could be tokens that can harm our loss decreasing. And they hypothesize that what if we can select tokens that can be learnable and they can help us to lower loss in more stable way. And they propose their new language modeling objective, which is called selective language modeling. And in this case, they just say that we pass all the tokens from the language model, but we select those tokens from which we want to pass gradients. And their pipeline is very straightforward. First of all, they need to find some high quality corpus, which is somehow correlated with our downstream task. And they train reference model on that high quality data set with standard causal language modeling. Just it. So now we have reference model, which already know what our tokens are important for domain knowledge. Then they pass all the pre-training corpus from that reference model and they calculated for each token their perplexities. So we have already pre-training corpus with calculated perplexities from reference model. Then the third step, we do normal pre-training with our pre-trained language model, but in each step we also we calculate also the cross entropy of that token, and we somehow understand and incorporate in each also the perplexity from the reference model. So for the step 3, they train tokens and they get only the tokens for gradient which have high excess loss, and identify excess loss as the difference between the perplexity for each token, which is coming from standard cross entropy loss from each token, and the loss from reference model. If this excess loss is higher from some threshold, they will take that for gradient. If not, they will skip that. And how they choose which excess loss to pass, they created this percent of which percent of excess losses in batch size you want to pass. And they just pass those tokens. So here is scoring function for each token. Is just this difference between standard loss and reward modeling loss. And if this loss is higher from from the percent that they want, it's in top K percent, then they will choose that token. Otherwise, they don't. So the percent,
8% of the differences
Mhm. So-
between reference and now.
so we have excess losses for all tokens, and we need to choose which ones to pass. And we just choose top K%, and top K% they just choose from ablation studies, and there is about 60%. It's just ablations. Like for BERT, they choose 15% where to put.
But they also scale the loss by 8%. Oh,
um,
to keep the learning rates constant. So if you have 100 tokens and you choose only 60 tokens, now you want to scale your gradient to be proportional of equivalence of 100 tokens. That's going to be bad. Okay, clever.
So
And there's something that reward modeling that comes from another model.
Yes, the reference, not reward. The reference model that is trained on high quality data.
who's
So you do two for.
yes, you do 2 forward pass and 1 backward pass. I don't know. They say that they are saving on training. But for forward pass, it is almost twice. So experimental setup for reference model, they train 2 kinds of reference models, one with mathematical domain and one for general domain. And they say that they get their data from high quality data sets. They train reference model for 3 epochs, and they choose for each domain 2 model sizes, 1 billion and 7 billion. And they also initialize their reference model from the same point as their continual pre-training model. And the continual pre-training model, they took data from, I don't know, Open Web Med. It's a not so high quality data set. And for general domain, they mixed general purpose corpus with code and with mod with these percents. They say that they use 32 H100s, and for the smallest model, they choose Tiny Llama 1 billion, and for largest model, they choose Mistral 7B. And they say that they usually pick 60% for token selection ratio. These are the results. So these are the few shot results, but for especially mod pre-training, let's start from here. So we have 2 models. The first model that they trained is Rho-1 mod, and Rho-1 mod starts from the same place as the Tiny Llama, but it's trained with selective language modeling, as these trains just with causal language modeling. And so Rho get less training tokens, but the results are comparable higher, and the average score is 16% higher than if you would train with regular language modeling. And if we compare with other baseline models, we see that 38% is not that bad, because maybe these models were trained on larger data sets, but they don't have the value here. And also they add that if they trained this with 4 more epochs, they will get like state-of-the-art result comparing to baseline models. With the same data, but 4 epochs, we will get. So this was the results for 1 billion model, and with 7 billion model, they also get gains with 10%. And also they say that this 66 accuracy is comparable with DeepSeek math metric, which is 68. And DeepMath get these results with 500 billion token training, and they got this result only with 10 billion token training.
This 10 billion was without
this was with selective language modeling, and this one wasn't. So comparable to this, the gains are 10%, 10%. And
The reference model standard.
this is the larger reference model. It is the 7 billion. If we use continual model 7 billion, the reference model also is 7 billion. So, and also they those were few short results. This is fine-tuned results. They fine-tuned with Torah data set, and they said that they also gain more accuracy with just continual pre-training.
Models from the previous slide, and
Then continue, they fine-tune with Torah, yeah. And also they use some tools. But these were on mod data sets. So if we go if we do the evaluations for general purpose evaluation benchmarks, we see that gains are much higher when there is a mod evaluation, but when there is not a mod evaluation, the gains are not so high. So let's start from here. These two are mod and GCM 8K. They are mod benchmarks. These two are Python coding evaluation benchmarks. These are code generation evaluations benchmarks. And in general purpose data set for pre-training, the third of them were for coding, and the 10% was for mod data set in the pre-training corpus. So if we get those kinds of gains, it's good. But for MMLU, we got gains, but like 40%, it's too low for MMLU because like DeepSeek RMAC is higher than 80% with absolute score. Yeah. But they are comparing only with Tiny Llama and with causal language model Tiny Llama, like.
Yeah, I think this is still good, but the ones below are not very.
Yeah, this one for reasoning task, this is general purpose, like exam tasks, like people doing for getting qualification. Like Winograd test is almost the same. So the gains are from this general purpose, with training this general purpose corpus is 10% overall average score. Now ablation studies and analysis. Can selective language modeling improve without high quality data? So if we give a reference model, if we don't in real life scenarios, we don't have high quality data to train a reference model. So what we can do with it, can we train our reference model on our pre-training set? And the key hypothesis that they say that maybe the SLM is not only good for aligning our data set to desired distribution, but maybe it is also filtering noisy data from our pre-training corpora, but this is just an hypothesis. And for that, I will explain this later. For that, they train their reference model on just pre-training corpora, and this is just regular or a model trained with causal language modeling. And below that is the language model that is trained with selective language modeling, but also using already trained reference models scores. And we see that the gains are not too much high, like 0.4%. So this means if the reference model is not so good at qualifying what is a good token and not, we don't get higher results on training with selective language modeling. So the gains and the average gains is like 2%. And also what they did, they say that what if we don't, for reference model, we don't use already trained reference model, but we just use normal information entropy. So how they call us scoring for scoring the next token information entropy. For each token, they just calculated like normal loss, and then they calculated the sum through all vocabulary tokens, and then they get one score, which will show how good is in terms of information the next token would be. And if they train with that reference, they get more higher loss than with using reference model with low quality. And if they use these two scoring functions together, they get a little bit higher result. So I'm mostly comparing GSM 8K. So we can compare these with values that we get when we use real reference model. For real reference model, we get almost 30 accuracy, but with low quality reference, we get just 6%, 6.7 accuracy. This is much lower. So what we can understand from this table is that using reference model with high quality data set is very important, because it's not only filter the data from noise, it also somehow guide our model which tokens are important for desired distribution for downstream tasks. Is that clear from here? This is the reference model which was trained with pre-training data.
OW and P5, they are relatively low for the reference. Right?
Yeah, for referencing themselves.
Their own data was GPT-4 generation, right?
Yeah. So the other ablation question is how selected tokens are correlated with downstream task loss. And this is the tokens dynamic in downstream task. So when we pre-train our model with 4 billion model. It's another ablation study. So we take our llama model and we continually pre-train it on 4 billion tokens. Then we evaluate. We also calculated the tokens of that downstream tasks, how they evolve, and took their average loss. Then we take our validation set and we filter out the tokens that are already selected from reference model and tokens that are not selected from reference model. So we first pass those our validation set through reference model and to our continual model, and we get which tokens will be selected, which ones are not. And then we see the training dynamics of selected and unselected tokens. When we train on 4 billion, we see that selecting tokens are getting lower loss. Meanwhile, the unselected tokens, they just don't train, and that's why their loss gets higher. And this is compared with baseline model, which was just a normal language model, and normal language model focuses on all tokens. That's why all tokens, even unselected ones, they they get lower losses somehow. But
validation set, right? But what does the selected and unselected mean in this case?
We have validation set, and we pass validation set through our continual pre-trained language model, and we can calculate excess losses for each token, and we can choose which ones are selected and which ones are not. Already we have those ones. And then we come back and start to train again our llama. We continually pre-train and see how those tokens evolve during pre-training. And so those are the dynamics. Selected tokens get lower and lower, and not selected tokens, they get higher losses. So they want to show the correlation between selected tokens and downstream tasks tokens. So we already see the correlation that they are aligned. This is the most ununderstandable image from the paper. They wanted to show some power law with selected tokens, and they took checkpoints from training on 2 billion up to 14 billion tokens, and for each checkpoint they calculated the losses for selected tokens. And also they calculated those checkpoints for some downstream tasks accuracy. And they see that if the losses for selected tokens get lower loss, the tokens get lower loss, those checkpoints also get higher accuracy on downstream tasks. So I can't explain what are those dots. I understand that that's like in one line, they could be checkpoints, and one of those checkpoints we can evaluate and understand the selected tokens loss, and then take that checkpoint and evaluate that checkpoint on some downstream task. But like these other points, I don't understand what are they. But they say that they found some power law with selected and unselected tokens.
This is on x-axis,
Mhm.
we have loss on the selected tokens. So if you pick the checkpoint, every color is one checkpoint.
Mhm.
And red is one checkpoint. So when I calculate,
So can I say that this is during pre-training? Like,
The loss gets smaller as you move to right.
Mhm.
For the selected, as you get a smaller loss, your downstream task accuracy grows. But for unselected, as you get a smaller loss, your downstream task accuracy decreases
yes.
for all the models. Like on
yeah,
the
but that's unselected, so it means it's negatively correlated with the other. On the left side, we have selected tokens.
yeah, maybe they are selling that our way of selecting model tokens is good.
Yeah, so they want to say that the loss on the selected tokens
It's correlated with the
is correlated with the downstream task, and the loss on the unselected tokens is not correlated or inversely correlated.
Yeah, and all for all model sizes.
This is not more exact. I think this is
These are the trained
Checkpoint.
checkpoints, like in how much data they were trained.
you have each checkpoint, I don't know, 10 billion, 8 billion. Why do you have multiple points? What other losses with that? I think it comes probably because this is few shots and for different samples of few shots it might be different. And
These are actually data points. So 2 billion after 2 billion steps, we take a bunch of unselected points, we measure the loss and accuracy, we just take them.
For every batch.
Maybe they took like 100 points of selected and unselected,
Mhm.
and over time they measured their loss and accuracy and we compares to them.
but what do you mean over time? That's the point.
After 2 billion steps, after 5 billion steps of training.
I think all of them are after to be like all value points.
Yeah, after two, I'm saying these points are actually like tokens.
Tokens.
They can split the test set into
Like they took 20 unselected and selected tokens. And over time, like after 2 billion steps, they measured their loss versus accuracy. And they showed that.
So what is the accuracy for one set of tokens? For measuring accuracy, you need the data set, right? Every accuracy.
That's weird. So it's a tricky picture. Reviewers asked about this reviewers asked about this picture, but the authors didn't answer to it, what they represent with these points.
No.
We can continue.
Second, we demonstrate that the loss of selected tokens
Can't we say that these points are checkpoints? And we measure the selected tokens after 2 billion with this checkpoint through training dynamics, through continual pre-training time?
The way I would do it is the following. I would take the test set, calculate. So this is few shot accuracy, right? Which means you have a context with few examples. And then you want to predict the result of the final one. So I take these few examples and calculate the loss on this cycle. It's one number, right? One loss. And the accuracy is either 1 or 0. I do this for all samples, all contexts. And then I group them according to their losses. Like I take 5 clusters, 1 beams of equal size. Like the easy ones, hard ones, medium ones. And for the ones with lower loss, I calculate the accuracy. For the ones with higher loss, I calculate the average accuracy and plot it. And be that for you. But they don't write about it. I check the mathematics.
So you have a training, another model that you're training and a reference model. Reference model is the same size. And you're training with that reference model.
What we are doing?
You are training the reference model.
On high quality data set, other.
The reference model is being called up there.
The reference model doesn't see any of those pre-training data. It just trained on high quality data. Then we take, another pre-training corpora, and reference model guides us through that pre-training to choose the tokens which will mostly align with downstream tasks, because that,
So they're not saving on they're just improving it.
they are saving on back propagation, but they
have trained a different model.
Because the first
They're not saving on.
the saving is because the high quality data set is much smaller than the pre-training corpora. That's why.
But if you don't say right, because you do 2 differences.
Yes. They say that the costly part is back propagation. But for you can, with reference model, you can do forward pass and save the scores. And during pre-training, you can just take those scores and don't waste too much compute on exactly pre-training time.
Do they have an application that they train their model with their normal loss on some data?
Yeah.
Which one?
This one, Tiny Llama CT, it's normal continual pre-training. This is with selective language model. This is normal language modeling.
Start from Tiny Llama?
They start from the same place.
So the original Tiny Llama is
so that's Tiny Llama, which
they train normally on this WM, they get 6. But if they train on WM with carefully removing the 2 things, they get much better.
you didn't mention that at all, but how much more computer less
Not in terms of more or less, just mention compute. They don't save on compute. They say that they save on filtering data. They made this data efficient, not compute efficient. It's at the end, I will show you how they sell their selective language modeling approach. And this is the simple power law that they say that for any loss on selected or unselected token, the loss is correlated with accuracy if it's selected tokens and inverse correlated with its unselected tokens. And this is the way how they choose that the best percent to take selected tokens is 60%. They just check the accuracy on some downstream tasks, and they see that 60%, if they select 60% of tokens, is the best they can take. It is the best result that they can take from downstream tasks. So this is the one that show their data efficiency. So this is the 1 billion model and 7 billion model. For 1 billion model, when they started from the same place with their selective model pre-training, they get the result much faster than with normal language modeling. They say 10 times faster they got on the same result. And if they train on 15 billion tokens, they bypass DeepSeek Math 1 billion's accuracy, and DeepSeek was trained on 150 billion tokens. So with 10 times less data, they can pass DeepSeek Math. And the same is with 7 billion model. Yeah. 7 billion is Mistral 7 billion. So if you are good, I can continue. Oh, sorry if you want. So limitations and future work. Scalability part, they say that they choose only smaller models, but what if the model is really very large? They say that they are not sure that with larger model they will get these results, because maybe larger models will already learn some inductive biases, how they can compress useful data. So they should do more ablations on larger models to see whether it's right for them or not. So is training on reference model, training reference model necessary with high quality data? And the answer is, of course, yes, because if we choose lower quality data or don't choose, it will not guide us with good tokens. And they say that we can even take like log probabilities from proprietary models APIs, and we can also get good amount of guidance from powerful models. And they also say how one can improve selective language modeling. They just, in their pre-training phase, they just choose tokens or don't choose, but they can also do reweighting of tokens. So not to do hard cutoff on them. They can use reference model as a reward model for reinforcement learning, and they also can adopt multiple reference models, because reference model is just like one domain guidance. You can have multiple of them. And where can else they suggest to use selective language modeling? So we see results on few short and one example on fine-tuning. They say that they believe they believe that it will help. Sorry. They believe that it will help on supervised fine-tuning. And also it will help on other multimodal pre-trainings, because with multimodal area, noise is much more. That's why if they use selective language modeling in multimodal setups, they will get much more gains. And thank you, and questions. Reference model performance if it's trained on continual per training setup. This is reference model on.
But this is on OWM, right? Not
Yeah. No, they don't show what is the performance on reference model with high quality data.
Maybe the reference model on the very small high quality data is already very good. Yeah, but this is because they claim a reference model with low quality data that doesn't work.
With high quality.
And already see the gap is really smaller than the 70.
So you don't think that it's a helpful approach for training? Which part?
We train the reference models for 3 blocks. All in experiment, we initially have to train our engine, the reference model with the same base model.
You mean why they use reference model if they can just fine tune it? Fine
No,
tune
we
it.
actually start from the reference model. But what is the base reference model score that we're going to do?
There is no information about that.
Good, right? Maybe it can be too bad because it's trained on very small. But somehow we have the knowledge to understand good programs are bad.
What are the signals of like defining this low to low, high to low, just to so that it's high to high and low to high being the training and the response speed?
That they will be tokens that like resist converging loss to lower values. So they just remove. No, they don't keep high to high. They keep only from high to low, because reference model will give only low value to which those tokens which have low value, and those ones are low to low and high to low. The reference, and the continual language model will give.
I have a feeling that the method they finally used to keep the token, this method is not one-to-one related to categorization. It is like a proxy for that.
I think the doctor is like one accuracy, but they want to go to these steps. They track the loss over time. Yes. Like let's see, all of these are on the same line. Then thinking is after 2 billion steps, they measure the loss the accuracies are the same. For their selected, non-selected or selected subsets, they measure the loss. And then after 5 billion steps, then after 8, 11, and 14. And that's how they got this curve. But all of these are on the same line because for GSM accuracy, they measured it on for after 14 billion steps, not for each of them. They are saying that these curves move in the direction for selected set, and the loss get smaller and
But that's also so you need that. But so what we do in aerial imagery, we use a very different algorithm to filter the data, and on one of the data sets we have seen something similar. We train on 50 times smaller data and get better results. By just removing from the
I think there is some proof that they show that their filtering method like only mathematics related tokens and detail.
And that's why it helps only once.
Like days and it probably helps because it gives most related data.
You notice that math and code directions are becoming kind of a separate topic. Math and code and everything else. And it's probably also easier to optimize for. I think when there was an evaluation of this latest third version of Quen, and it's very good at math and coding. But then there was a very hard data set from OpenAI about question answering, complicated questions unrelated to math. And then this question answering, Quen model is very tough. It doesn't memorize. But it can relearn math. Solve problems. I think it's something to learn that these are very different things.
I think Martin did holding on 0 to the level of synthetic plus turning it all in. So for a long time, these models we often look for biology discovered, but
How do you solve difference on data duration? In our case, we do this filtering based on China version 2 vectors of images. It kind of acts as a reference model for us, right? We pass it to China, these vectors, but it's not to us. We are just looking at the individual business. Transferring of the vectors. maybe use the same here, like have a model around on the corpus, do the clustering on the corpus, and then only those tokens that pass the filtering. Okay.
That's a one clever trick from the one paper where they collected different mathematics data set. And so they started with the very thin data set. They trained them, classifying it, and then they predicted on the 30 data set that was like orders of magnitude larger. They took the most confident, like 1%, and added it on top of the original data set and iterated it.
But again, we know but without the last learning, so we will be the then we can do the opposite. We can bring the clustering idea to here.
But with text, can we incorporate clustering idea? But we will choose tokens, but we need to choose sentences and then.
No, we will take the vectors of the words conditioned on the context. So you just do forward pass on the entire document for every document. You have one vector, but this vector is contextualized. It already.
I see.
And then we use vectors in the clustering, keep the 10%. And then do another round of training. We did have code.
Yes, they have code and also public DF2 models on Hugging Face.
Right now, I think.
Someone asked about this figure, and with selected and unselected tokens, and they haven't yet answered to it in open review.
Like why access is based because still the accuracy after the family, but the loss can be something.
But how they choose those tokens and like
Like,
in
yeah.
validation set and for like downstream tasks?
You just selected the last couple, selected the last tokens, they keep track of the errors over time.
And how?
After the training, they promote the accuracy. The ones that accuracy is for the specific token after on some specific check.
I think the one thing that they have in common is the checkpoint, like validation set and accuracy on downstream task, and these are the checkpoints. And checkpoints are evaluated with some data points in validation set, and
To extend the lines, they are on the same level.
yeah.
And several data on each checkpoint. There's one point on the same line. I mean, like, look at these are all on the same exact line. These are also on the same line. So all of these have the same accuracy. So this is the same data point over when they should retraining those decreases for this data point. The relation between accuracy and loss is inverse, and here it's correct.
I understand x-axis, but how do you understand it with accuracy?
Accuracy is what you get after the training.
On what?
On the downstream process.
But you aren't training. You just train your data on some pre-training data and evaluate on validation set on.
Pre-training.
I think no. These are the losses from. This is from validation set. This is from downstream accuracy.
Yes.
So this is from validation set.
In training of pre-training paper, you measure on validation set.
Yes.
Both selective and unselective
Mhm.
subsets for a couple of data points. Each line here is a different data point over time.
Data point, you mean one token?
Yes, probably not. The one y-axis is the accuracy after the training of the.
It's one token. Other questions? Thank you too.